my session. My name is Daniel Shih from National Taiwan University, Taipei, Taiwan. The title of this paper is Superpixel Tracking. It's a configurable polynomial-time semantic segmentation for endoscope video. The goal of this work is to support the mixed reality for endoscope surgery. I think many of you have seen the work to provide additional information for the surgeon during the operation. As you see on the right-hand side of the slide, we are already overlap additional information on top of endoscope image. But most of the time, this kind of information are shown on the separate display in the operation room, which actually is the extra mental load for the surgeon. So there are many efforts try to build a augmented reality or mixed reality service for the surgeon, so they can obtain additional information on the single view. However, the major challenge is overlapping the information on top of this endoscope image require accurate localization, registration, and tracking, which is not trivial, and that is the main goal of our work. So this picture shows you the data flow for the to support the aforementioned goal. So we'll be given the image from the endoscope, shown on the top left-hand side, which may have smoke and the reflection. Then we need to do a desmoke and to remove smoke from image. After we remove the smoke from the image, then we can do the segmentation, we can do the tracking, we can do the SLAM, and also we can use that image to obtain the depth information to allow us to do the SLAM-driven registration, so we can know where is the camera inside the human body. Based on this localization and the tracking result, then we can overlap those additional information on top of endoscope image. Okay, so on this paper, so actually we are talking about, we will focus on this part to provide real-time segmentation to track the label result. So on this paper, we are given the input, which is the endoscope image. Then what we want to do is generate the semantic segmentation result of this endoscope image in real time. So you want to minimize the GPU utilization to generate this label, to label this image, while the MIOU will not decrease for more than 5%. And the proposed method will track the superpixel instead of pixel. Superpixel are the cluster of pixel to label every pixel on the image. Okay, so this figure on the slide shows the flow of our proposed method. So we have a frame image from endoscope camera, and we will first do a pre-processing using the simple linear iterative clustering to cluster pixel into the superpixel. Okay, based on the superpixel result, we will make a decision if this superpixel image is a keyframe or not. Keyframe means that we are not the superpixel tracking method will not be able to track the semantic segmentation label. Then we need to conduct the traditional semantic segmentation. So if it is a keyframe, then we need to use a baseline model to label every pixel on this image. Okay, if not, then we can continue. We can apply our superpixel tracking method to reduce the computation workload to label the pixel on the image. Okay, let me show you how we process the keyframe. For each image, we'll be given a raw image. Then we will use the slick iterative clustering method to find a superpixel for every pixel on the image. Then for the keyframe, the image will be given to the semantic segmentation algorithm, for example, the DeepLab V3, to label each pixel. Then we will merge these two results, the label, the pixel, and the superpixel into the result you see on the right-hand side. then this will be given to superpixel tracking algorithm. Okay. When the frame is not a keyframe, we apply the superpixel tracking. So for each frame, we will have the superpixel. Then for each superpixel, we will try to find a label for this superpixel. The way we do is we define search range to on the previous frame. And on this previous frame, we will find a superpixel which has the shortest distance in terms of color and location, and to use its label as a label for the new superpixel on the current frame. Then we will finish the tracking process. The V3, and this column shows the superpixel tracking accuracy. The last row is the superpixel tracking with our keyframe. You can see on these three columns, the accuracy is pretty much similar. But the important thing is the baseline uses every frame as a keyframe. That means they will conduct a semantic segmentation on every frame. But for superpixel tracking, we only use 13% of a frame as a keyframe to track. But ST without keyframe, which of course use no keyframe, but accuracy is much lower than the previous two. This slide shows you the comparison of the 14-point operation. As you can see, when we use the 480 times 480 as a baseline, we can see that when we use the baseline, actually the computation workload is 25,000 times more than the superpixel tracking. If we use the low computation complexity algorithm for semantic segmentation, we still require 5,000 up to 6,000 times of computation to have a similar result. So in summary, we propose this superpixel tracking algorithm to track semantic segmentation result. We minimize the use of computation